Hello once again, class, and welcome to another mock lecture. In this video, we are going to talk about the derivative as a function. Now, we just finished talking about the derivative at a point. We learned that the limit definition of a derivative at a point is given to be this f prime of a is equal to the limit as h approaches 0 of essentially the difference quotient at a point a, provided that this limit exists. Well, we can use this same definition to define a function. If you think about all the values of a, right, that you can plug into the derivative at a point as the inputs of a function, then the output, f prime of a, is basically describing the function's slope. So you have this sort of input-output relationship, and each point that you plug into the derivative is going to give you one specific number, namely the slope of the graph at that point. So this is the derivative definition in terms of a function. It's the limit definition of a derivative as a function. It says let f be a function, then f prime of x is also a function, and it's given by f prime of x is equal to this kind of definition of a limit that we're used to, but instead of a, right, instead of defining it at a point, we're defining it for all x. And it has the domain all x values such that f prime of x exists. And that's really important because, as we're going to find out soon, there are some x values that exist in the domain of the f function, but actually f prime of x does not exist. But basically, the concept image that you should have of this function is that f prime of x is a function of all the slopes at every point of f of x. F of x does what it's going to do, like imagine a polynomial. It's got different slopes at every instance of x. Every x value is going to produce a different slope. That slope is the output for f prime of x. So the main idea, f prime of x is a graph of f of x's slopes. So let's do a couple examples. All right, suppose we wanted to know what f prime of x looks like given this f of x graph. Okay, so this is looks like some quartic function, right, f of x. And I want to figure out what does the graph of its slopes look like? Okay, so remember, what we're trying to graph is the slope of this thing over the same x values. So keep that in mind. Always keep in mind f prime is the slope of f. So there's three things that I think are really important to remember, to really examine when you're given the graph of f and you're trying to graph the graph of f prime of x. First thing is, where is the slope of f of x 0? Okay, for polynomial stuff, that's going to be, or really kind of, rational stuff, we'll do this too. You want to look for where the function is changing its slope from positive to negative or from negative to positive in a non-asymptotic discontinuity situation. Basically, what I'm trying to say is you need to look for where the graph has turning points. That's typically where your function is going to have a slope of 0. It's where all the tangent lines at that point have a slope of 0. And in this particular graph, there's 3 locations, I would say. So what that's going to mean as far as our derivative function goes is that those are going to be x-intercepts. It's where the slope is 0. So of course, the graph of all of our slopes of f are going to have a value of 0, a y value of 0, because the slope is 0 there. For the main function, the derivative function is going to have x-intercepts anywhere the function has a slope of 0. The second thing I do is I ask myself, well, where is f of x increasing? This is where our function is going to be positive, above the x-axis. And by function, I mean this is where our derivative function is going to be positive or above the x-axis. On this example, it looks like from 0 to 2, we've got some positive slope for f. And then from 3 to infinity, right, we're going to have some positive slope there. It's where the graph is increasing. But what that translates to as far as the derivative function goes is that these are the intervals where f prime of x is positive, and what I mean by that is it's above the x-axis. The other side of this coin is we need to figure out, and this is the third thing, where is f of x decreasing? I mean, for polynomial functions, it's decreasing on the intervals that it's not increasing on. So in this case, it's just the other 2 intervals that exist here, namely negative infinity to 0 and 2 to 3 are where the function has negative slope, and that's going to be where our f prime function, the derivative function, is below the x-axis. And if you keep these things in mind, right, it has to have intersections at these points, has to be above the x-axis, but then dip below the x-axis in the blue spots and then dip back above the x-axis in the purple spots. then you kind of only have really one way to draw this thing, and it would be like this. So it's adhering to all these rules that we've kind of instantiated here. Where the slope is 0, that's the derivative's x-intercepts, right? And that happens at 3 different places. Where the slope is positive, that's where the derivative function is above the x-axis, where it is actually positive. And where the main function has a slope that's negative, where it's decreasing, that's where the derivative is going to be below the x-axis. So again, always remember, f prime of x is the graph of all the different slopes that f of x has at the same x values. So you can think about f prime as a graph of all the tangent line slopes at every point on f. Now, of course, in that example, we were given a graph, so we had to examine it to figure out what the derivative function looks like. But in this next example, suppose you're just given the function equation and you're asked to graph the derivative. Well, then in this case, we could actually just find the derivative, right? We have the limit definition of a derivative, so we could just use that. So let's say that g of x is equal to x cubed minus x plus 1. We could just simply find g prime, right? We know how the derivative is defined as a function. So this is, and I'm not going to go through this whole thing. Here it is for you. You can look at it, pause the video. But essentially, you're going to find that when you use the limit definition of a derivative for g, you end up with 3x squared minus 1. And that thing is the graph for all of the slopes of the tangent lines at every point on g of x. Okay, so then I would just draw that. The red function here is my g of x. The blue function is g prime. And again, notice it's still behaving like a derivative. Where g has a slope of 0, that's where g prime is intersecting the x-axis. Where g prime is below the x-axis, that's where g has negative slope. Right? So all of these things are still consistent. Even though we didn't graph based on the base function, we actually just took the derivative and I graphed them. But look, it's still behaving like we would expect, like the first example, right, was behaving. So let's go ahead and define where a function is differentiable. Like when is a function differentiable at a point, meaning that its derivative exists at that specific point. So this is the definition of being differentiable at a. It says a function is differentiable at a if f prime exists. Pretty straightforward. And it is differentiable on an open interval a to b if it is differentiable for any value on that interval. Here I'm calling it k. So pick a k value between a and b. It's going to be, if it's differentiable for all of them, then we would say it's differentiable on that open interval from a to b, bounded by a to b. Now, because continuity and differentiability are both based on limits, it's very tempting to think that differentiability and continuity have this biconditional implication relationship, to say that differentiability implies continuity and continuity implies differentiability. And what I mean by that is if you know a function is continuous on a specific interval, can we say, well, then its derivative also exists wherever it's continuous? It's very tempting to think that this is true, but let's examine it. First, we're going to go this direction. We're going to look at, does differentiability imply continuity? Meaning, if you know a function is differentiable at a specific point, can we also then assume that it's continuous at that point? Well, let's take a look. Let's assume that f of x is differentiable. Basic if-then strategy. Assume the hypothesis, and then we're going to try to prove the conclusion here. If something's differentiable, we get this for free. That's the limit definition of a derivative at a point. Assume f of x is differentiable at a, therefore f prime of a is the limit definition of a derivative at a point. Now, by the way, and I think that this is worth talking about, there is an alternative way to write the limit definition of a derivative. I have gone with so far just the difference quotient method, but you can actually write it in terms of something that looks more like slope. If you let x be equal to a plus h, then you get that h can be replaced with x minus a. And that looks more like a denominator that you'd see for slope, right? x1 minus x2, or depending on how you're writing it, you might know it as x2 minus x1. So if we do that, right, then the only way that h can approach 0 is if x approaches a. We can't have a approach x. A is a constant. We know a is the point we're trying to find that it's continuous at in this example, or in this proof. So x is the only thing that can change. So we have to have x approaching a. That would be the only way for this thing that I'm putting a box around to be 0, and that's what h is supposed to be approaching. So I'm going to replace this, right? Another way, an alternative way to write the limit definition of a derivative is the limit as x approaches a of f of x minus f of a over x minus a is what we decided h was. Okay, so this is what I'm going to use for this proof. I'm going to use this limit definition of a derivative. Now, if we want to show continuity, we need to show this. We need to show that the limit as x approaches a of f of x is equal to f of a, which means that there's no removable discontinuity or something like that, right? The values that we're approaching from the left and from the right, whatever they're approaching, well, the thing is actually that particular value. That's what makes it continuous. That's what this is saying. Now, you might be wondering, hang on, Mark, I remember your video on continuity, and there were 3 things that had to be satisfied in order for something to be continuous. This was the last one. The first one was that f of a had to be defined, and the second one was that the limit as x approaches a of f of x even exists in the first place. And you know what? You're absolutely right. We do need to show those things. But we get them for free here, and that is because f of x is differentiable. If f of x is differentiable, we know this exists. And in order for this limit to exist, f of a has to be defined. It shows up in the limit. F of x, right? The limit as x approaches a of f of x has to exist. Those things need to be true in order for f prime to even be a thing here. So these are already satisfied, which means the only thing we need to show to prove that this thing is continuous at a is the limit as x approaches a of f of x is equal to f of a. All right, so here's how this proof is going to start. We're going to start with just the expression f of x minus f of a. And what I'm going to do to this thing is divide by x minus a. And if I divide by x minus a, I also need to multiply by x minus a. Essentially what I'm going to be doing is unreducing it. Technically, it's a fraction. It's f of x minus f of a times 1, and I'm just going to multiply by x minus a over x minus a. Which again, we can do because this is just the number 1. Now, of course, I am making a small assumption here. I'm assuming that x minus a is not 0. That's what we're approaching. So by doing this multiplication, I'm kind of assuming we're not, x is not a when I do this multiplication. Okay, so I've got this. I've chose to written it actually like this, where I wrote x minus a in the denominator for here, and then I just wrote a multiplication kind of outside that fraction. Well, if these two things are equal, then their limits are equal. The limit as x approaches a of the left-hand side of this equation should be equal to the limit as x approaches a of the right-hand side of the equation. And now I'm going to focus here. First, I'm going to use the product rule for limits. So I have applied the limit to the first part of the product. If I go back a slide, I applied the limit to this part, and then I applied the limit to this part, and I'm multiplying them. That's just the product law for limits. This thing is just f prime of a. So I'm going to replace that with f prime of a. And then this is 0, just by direct substitution, right? There's nothing stopping me now from just plugging in a for this x. You get a minus a, that's 0. And so we have 0. So what we know is that this thing equal to 0. Equal to 0. Okay, so I'm going to store that in the memory banks up here. That's going to be important for later. What I'm going to do now is I'm going to focus on this. I want to start here, and I want to get to f of a. That's what I need to show. I need to show that this thing reduces to f of a. Now here's something pretty cool. The limit as x approaches a of f of x is the same as the limit as x approaches a of f of x plus f of a minus f of a. This is 0. I'm adding something, but also subtracting something. It's just like saying 4 is equal to 4 plus 10 minus 10, right? I can do that. So that's what I'm doing here. Kind of this fancy addition and subtraction. But then I'm going to reorder it. Addition is commutative, and subtraction is just the addition of a negative. So I can still move it around as long as I keep the sign the same. So that's what I did. I took this f of a, brought it out here, and then I wrote, oh, well, that's the same as f of a plus f of x minus f of a. So essentially I just switch these location via the commutative property, and then by the associative property, I've chosen to group these ones together first. Well, now it's set up so that we can just perform the sum law for limits, right? I can apply the limit to f of a. I can apply the limit to f of x minus f of a, and I would get something that looks like this. But then it's at this point we have to remember that thing we stored in the memory banks. We already showed this limit is 0. The limit as x approaches a of f of a is just f of a. There's no x in it. So this is essentially a constant. It's whatever the output of f is at the point a, so that's just f of a. So we get that this limit, right, both of these limits when added together is the same as f of a plus 0, which is equal to f of a. So we started here, limit as x approaches a of f of x is just f of a. And that's what we needed to show for continuity. So therefore we can conclude that if something's differentiable, then at a point a, then it's continuous at that point a as well. So now let's look at the converse. Does continuity imply differentiability, right? If a function is continuous at a point a, is it also differentiable at a point a? No, it's not. What is true is that not all functions are differentiable on their entire domains, which I guess another way that I could say that is not all functions are differentiable where they are continuous, right? We know that all the basic trig functions and basic precalc functions are continuous on their entire domains. So another way that we could think about this is no, not all functions are differentiable where they are continuous. And as my counterexample, right, for this, right, continuity implying differentiability, let's consider this v of x function, which is just the absolute value. The absolute value function is defined to be negative x if x is less than 0, and it's defined to be x if x is greater than or equal to 0. So basically, it turns, the output is always positive. If x is negative, right, less than 0, like negative 10, then you plug negative 10 into this thing, it becomes negative 10. That's the worst 10 I've ever drawn in my life. But then that's positive 10, right? Negative 10 is positive 10. So the graph looks like this. It's always positive. Now, it's really easy to show. Really straightforward, I think is probably the right word to use there. It's pretty straightforward to prove that the derivative exists on these two intervals, when x is less than 0 and when x is greater than 0. Here are, in fact, the proofs for that. Granted, there's no justification for any of this stuff, but this is how the proof would go. I'll let you look at it if you'd like. You can pause it here to see kind of what's going on. But it's when x is equal to 0 that something poses a problem. We have a problem when x is equal to 0. What we would need to show is that the limit as h approaches 0 of 0 plus h in an absolute value function minus the absolute value of 0 over h, which actually just simplifies because 0 plus h is just the absolute value of h, minus the absolute value of 0, which is just 0. So it's just the absolute value of h over h. We need to show that this exists. Now you might be wondering, what the heck is this? Where am I getting these zeros from? Well, remember, I'm trying to show differentiability at 0. So I'm trying to find f prime of 0, which is this whole thing. That is f prime of 0. Normally we would say a plus h and then minus f of a, but a is 0. So I'm saying 0 plus h minus v of 0, which is the absolute value of 0, all divided by h. But again, that just simplifies to being this limit. So we need to show that this limit exists. How do you show a limit exists? Well, the left-hand limit and the right-hand limit have to agree. So let's do that. The left side limit, right? The limit as h approaches 0 from the left. So from this direction of the graph, we're approaching 0. Well, that's the same as the limit as h approaches 0 from the left of negative h, because we're here, we're approaching from the left, and the definition of absolute value is negative. So we got negative h divided by h, which is negative 1. So, okay, the limit as h approaches 0 from the left is negative 1, which actually makes sense. I mean, the slope for this whole side of the graph is down 1 over 1, right? So negative 1. What about the right-hand side limit? Well, that one is the limit as h approaches 0 from the right of the absolute value of h divided by h. But then we're here. We're in this part of the definition of the absolute value. So the absolute value of h, being that h is positive here, will just be h, right? That's why I wrote just an h here. H divided by h is positive 1, so these don't agree. The left-hand limit and the right-hand limit do not agree, which means this limit does not exist. That limit is f prime of 0. So no, f prime of 0 is not differentiable, or rather, I should say, really I should also say v of x. V prime of 0 does not exist, even though v of x is continuous at 0, right? And that's really the main thing. We know it's continuous. I mean, look at it. It's definitely continuous. The limit as x approaches 0 is the same as the limit from the left is the same as the limit as x approaches 0 from the right. They're both approaching 0. And also v of 0 is 0. So we've satisfied all the criteria for this to be continuous, and yet we find that it's not differentiable. And it's really because the slope has this kind of instantaneous change from being negative to positive. And any time that you have a corner like that, then your function's not going to be differentiable. So there are three main ways that a function could be non-differentiable, and the first is a corner like this, like an absolute value function. Anytime this slope instantly changes like that, from negative to positive, from positive to negative, then you have something that's non-differentiable. You've created this jagged corner, very sharp corner, and the function's not differentiable there. The second way, actually we already know. It's when your function has a discontinuity at that particular point. It's really the contrapositive of the differentiability implies continuity statement. The contrapositive being if something's not continuous, then it's not differentiable. Right? That's just the logical contrapositive. It's always true when you know that some if-then statement is true. So, okay, there's three different types of discontinuity. Jump discontinuity. So this particular function, not differentiable at whatever that x value is. Asymptotic discontinuity, right? Function's not differentiable at that particular discontinuity. Removable discontinuity, function's not going to be differentiable at that removable discontinuity. Anywhere it's not continuous, right, it's also not going to be differentiable. The third way is when there exists a type of vertical tangent line, right? Whenever your derivative, your tangent line is vertical, it has a slope that's undefined. So of course your function wouldn't be differentiable when you get something undefined as the output. Right? When you plug something in and you're getting something undefined, your function is not defined there, so we wouldn't know how to graph it. An example of this happening, right, whenever the limit of the derivative, so we're talking about the limit of the secant line is really what this is saying here. But whenever that's plus or minus infinity, that means there's some kind of infinite discontinuity happening at a for the derivative, which is the graph of the slopes of the original function. So those are the three main ways that a function is non-differentiable. The thing I want to end this video on is just a quick difference of notation. So this entire time we've been using what's known as Lagrange notation. That's the f prime of x, f double prime of x, f triple prime of x, and these are higher order derivatives, which our next video is going to be over. So we're going to talk about that really soon. But right now, it's the kind of main usefulness of seeing this is really that, it's a function, right? You plug in an x, you get a slope. Or you plug in an x and you get a velocity, or an acceleration. Or you plug in an x and you get the jerk. And that's what these things would mean in a physics sort of context. But we're assigning it the normal input-output kind of relationship view that we're used to seeing for functions. But there is another notation that's very useful. And by the way, you could also say this as like y prime, y double prime, y triple prime. If your function's just defined to be like y is equal to some stuff, then y prime would be the slopes, right, of that particular graph. But there is another notation that's going to be useful pretty soon here. And the way that we are going to use this next notation is more of like an operator sort of thing. And this is Leibniz notation. And it looks like this. dy over dx, that's the first derivative. D squared y over dx squared, that's the second derivative. D cubed y over dx cubed, that's the third derivative. And of course, we could keep having higher order derivatives here. But in this notation, d over dx is an operator. It's the same as like if you're going to square both sides. You could just take the derivative of both sides, right? So this is implying that you're doing something to a function or to an expression. So it's working as an operator. So for example, if you have f of x is equal to x squared plus 1, and you wanted to then take the derivative of both sides, you could do that by just running both sides through the operator d over dx. So then you'd get d over dx f of x, that's like your derivative. Right? If you think about f of x as y, that's where you get dy dx. And then over here, you're taking the derivative with respect to x. That's what the dx part means. We're going to use this a lot once we get into implicit differentiation. Start doing a lot of related rate stuff towards the end of the video series for Calc 1. But it is important to have something that can act as an operator. So like showing that we're taking the derivative. If you could still use it to plug in stuff, like, for Lagrange notation, it's very easy to say, well, let's evaluate the derivative at the point A, because it's just plugging it into a function. And that's easy to see with Lagrange notation. It's not like you can't do that with this Leibniz notation either, though. If you have the derivative, you can put this big vertical bar, and down as a subscript, you can say, oh, let's evaluate it at x is equal to A. And those would mean the same thing in this context. So that's it for this video. If you guys have any questions, please leave a comment below or send me an email. Thanks a ton for watching, and I'll see you in the next one.